Hello, how are you? I hope you're doing good. I am doing good too. Welcome to today's class. Today we are looking at the column design, the design of reinforced concrete columns. In the last class we looked at the column design criteria, and today we're just going to look at a case study where we're going to design a column to a reinforced concrete column to British Standard, and we are going to run or carry out the necessary checks and find out how to design such a column. So I hope you will learn a lot, and if you've not watched the previous video, it's better you watch it. The video titled the column design criteria, you better watch it so that it can guide you on what to do before you come to this one. I would like before I start designing the column, first of all I would like to highlight the column design criteria as we stated in the next class, and we listed a number of steps, that is from step number 1 to 9, as you can observe them on your screen. For step 1, you carry out an analysis, and we had discussed this, that you need to either do manual design calculations where you analyze your structure manually, or you can use a modeling software to carry out an analysis. And there are many modeling softwares existing in the market, including Prota Structures, Teclateds, Master Series, eTabs, Stad Pro, you have Procon, you have Midas, and many others. So you can pick one which you think can suit your purpose, and kindly ensure you always have genuine licenses for these softwares, because if you don't have a genuine license, there are things you miss out on, and it is also not good to have the pirated ones. So having analyzed your column, and you have your design moments, and you have your axial loads, you also classify it in terms of whether it's braced or unbraced, and that is the end to step 1. For step 2, as we stated, you need to classify it in terms of its slenderness, after which you determine the cover depending on the fire considerations and exposure conditions of your element. And then for step 4, we now dwelt with the design of short columns, where we divided it into 3 cases, where for case number 1 is where there are no significant moments from analysis. Case number 2, it's for columns that support continuous beams, where analysis does not allow us to frame it into columns. And for case number 3, now we design columns that are subjected to uniaxial moments and direct loads. And for this case number 3 is the one we also use for the design of slender columns. So for the slender columns, that is step number 5. We have stated that they are designed like case 3, and you also need to consider the additional moments that are as a result of the column's slenderness, and add it to these initial moments you obtain here in case 3, so that you obtain the design moments of your column. So for case number 4 and 5, it's not that you have to carry out these 2 cases, but depending on the classification of your column, as we stated here in step 2, you either use 4, and for 4 you either use any of the cases, and if it's 5, you use case 3 of design of short columns, and then you add the initial moment due to slenderness. This is where actually many people give up when learning on the design of columns, because those moments seem they look like they are very hard to find, but today we are going to realize that they are very easy to determine. Next, now you move to the design of columns to biaxial bending and direct load. That is after obtaining the maximum design moments. Now you design it and provide for reinforcement, and check whether the concrete class and section provided is sufficient. After which you check for minimum reinforcement and maximum reinforcement, and then you also check for reinforcement containment. And it does not stop here. After designing, you also need to go to site to ensure that issues like reinforcement, containment, vibration or compacting of your concrete. You also need to supervise the work to ensure that they construct on site that which has been designed for. So that is briefly, that is the column design criteria, and if you have not watched it, you can watch it from our previous video as we have explained very well. So today we are actually going through the entire process, and we will also show you the reference that is used when we designing columns, and we are going to use them and actually have a look at them. Before this, you need to have this code. This is the British Standard, which is the structural use of concrete, part 1. That is the code of practice for design and construction. And then you see this is the version that was released in 1997, and this is one of the codes we use in column design. The second one is the structural use of concrete. That is still British Standard 8110, but now we use part 3. What do we use part 3 for? Just as highlighted in the previous video, part 3 contains design charts for singly reinforced beams, doubly reinforced beams, and rectangular columns, as we will see in today's class. And then these two codes, when you look at the British Standard, are very, very instrumental when it comes to the design of columns. So the very first step is identification of your column, and here we are designing a column at grid F9. That means our grid intersect at F9, and this is it's very important for you to label so that we know the location of your grid, and we can counter check it with the drawing you provide, so that we able to identify the column, and if we want to carry out checks to find out whether your work is okay, we can do that. So labeling of your column is very key. Don't just design a column that we cannot see where is it when you give us your drawing. Before you start designing, there are general assumptions that you can make. One of the assumptions is that the general condition of clause 3.8.1 are applicable, as we saw in the last class, but we can go back there. 3.8.1. Let me show you how, if you want to get to columns, you look at the contents of our code. There they are. And in the contents, the first section is general, the second is design objective and general considerations, the third is design and detailing of reinforced concrete, and the fourth is design and detailing of pre-stressed concrete. So because we're looking at reinforced, we're not yet looking at pre-stressed. You now look at if you're doing beams, you get beams here, and then it starts from page 23. But for now we are interested in columns, and columns is 3.8, which is from page 59. So from page 59 is where you're going to focus on. But there are clauses that are not provided here, which you get them in other elements, but they are also beneficial when it comes to columns. Just like the formula for checking of the shear capacity of a column, it is the same, because a column is a concrete element. So we get to columns. Which page was that? Yes, here it is. So clause 3.8.1 states that the provisions, let me increase this, maybe it's not legible. The provisions of this clause relate to columns whose greater overall cross-sectional dimension does not exceed 4 times its smaller dimension. So a column is an element whose one dimension is not 4 times greater than the other dimension. Otherwise, it could be called a wall. If one dimension is greater than the other, when you look at the cross-section of that column, then it ceases to be a column, and we design it like a wall. So first of all, we need to ensure that if we're designing a column, it meets this specification. The second specification is that while the provisions relate primarily to rectangular cross sections, as we saw even during the in the charts, they talked about rectangular columns. The principles involved may be applied to other shapes where appropriate. So you can also apply them to circular shapes, as we will also see where the code states that these can be used for circular shape. So we can also use them for other shapes that may be irregularly shaped, trapeziums and all that, because the principles are the same. So having stated that the general conditions are met, the column is also assumed to be symmetrically reinforced, and the specified design axial loads include the column self weight. And in your design software, you need to study it carefully to ensure that whatever information it's giving you, it includes the self weight of your column, or if it's not included, then you need to include it manually after obtaining the total loads from your structure to the column. Lastly, one of the last assumptions is that the design axial loads are taken constant over the height of the column. So because it is actually an assumption, it is not entirely true, but it's an assumption we make so that we can design the column, because once you're designing the column, the loads at the top and the loads at the bottom are not the same. But we need to make also this assumption, because we will be considering moments at the top and moments at the bottom, and we will be subjecting them to the same axial loading, which is the axial loading that the column is carrying. So that is also an assumption that is very key to make. Now from analysis, that is subprime analysis by an analysis software, you can obtain your dead loads and live loads and even your load summations depending on the factors that you have input there. And also there is an important aspect here that I have stated, that and ignoring the axial contribution of lateral loads. After 3D analysis for purposes of this calculation, the loads were summarized as shown here. The column size was assumed to be 200 mm by 300 mm, and for us to size this column this way, we look at the architectural drawing. The architect does not want, he has 200 mm thick walls. He does not want columns extruding outside the walls. He wants columns that are hidden inside walls. So that is why our column is 200 mm in one dimension. And then for the 300 mm, it is along the wall. So for that, we have an allowance of increasing it to to a bigger cross section by altering this 300 millimeters. And we can see when we will be designing this column, if it fails, if maybe the size is small, then we will increase this so that we have a bigger column in one dimension. This is basically because of the architectural considerations and the aesthetics of our structure. And as an engineer, many engineers sometimes do not factor into this. This into practice is a thing that we need to do, because architects also need to see whatever they have designed or contemplated being the actual thing that is actuated on site. So the column loads are QK is 59 kilonewtons and GK is 616 kilonewtons. And I can show as a summary of those loads from a design software. So here we have, these are columns, and actually we have load case, that is L1 up to L6, and then we have load combination 1, 2 and 3. So in this case, what I'm interested in are the dead loads and the live loads, and combination C1, because these are more important. But if I have my dead loads and live loads, I'm able to proceed and do my combination without depending on the software. So we were looking at column number, in our model it was column number 13. There it is. And we stated that for L1 it's dead loads, for L4 it's live loads. So for column number 13, L1 is dead loads, that is 615.2836. So if we can go back, you can see 616 kilo newtons. There, yes. So we have just truncated it to 616 so that we can have a simple value to work with. And for L4, which was the live load or the variable action, it was 59.0. So you can also see it is here 59 kilonewtons. So we have obtained our column loads. Now we need to sum up our column loads so that we can be able to get design loading. For design loading, we need to determine SLS. Remember, SLS will be useful when we'll be designing pad footings. We need this so that we can size that pad footing. So though in the design of a column, this is not that helpful unless you want to check its behavior under serviceability. So when you sum them up, you get 675 kilonewtons. SLS is pretty easy. You just multiply your dead and live loads by 1, and then you sum them up. You get 675 kilonewtons. And then under ultimate limit states, you use a factor of 1.4 and 1.6, as we can see from the code. That is close to it's normally around 2.4. Let's see. Where is that? Yeah, 2.4.3 values of loads for ultimate limit state. And in this case, we use 1.4 and 1.6 for dead and impost, and that is for the adverse conditions. So yeah, that is what you do. When you sum them up, you get 956.8 kilonewtons. So let's just go back to our loadings. And then you can realize that we have 955.85 as our combination 1, and this is the ULS combination in this application. So I hope you appreciate that. And also you can note we have combination 3, 682, and here this is 675, so they are almost the same. But I normally prefer, if I'm doing manual calculations, I get the actual dead and live loads, and then I do my combination independently so that I can counter check what that design software has done for me. And then next we have moments and shear at the ground floor. That is the where we are designing this column on. We're designing the column at the ground floor. And let me state something at this point, that when you're designing a column, you need to calculate its loading from the top to the ground floor. And sometimes designing the column at the ground floor is not does not give a true account of what you're working with, because sometimes we have floating foundations or the columns below the ground floor level are very long or very slender because we have a very big foundation depth, to the point that they have extra induced moments, and they also carry the weight of the ground floor. That is basically for suspended floors. So in that case, it is good you include the loading of the ground floor to that column. But in this our case, we assumed that our foundation was shallow, and we designed our column at the ground floor. And the same reinforcement used at the ground floor is the same reinforcement that goes to the substructure, that is the foundation. So also getting shear and moments at the ground floor, that is VXX, VYY, and MXX, MYY. So our column was this C13, and then you can observe we have our moments. Where was that? Right here, I believe. Yes, because now these has already been combined. This one, yeah. So we have moments M22, that is 85.6, and M33, that is 1.4. So you see these are the moments that we're going to use in our design. That is 85.6 and then 1.4. And then for shear we have 81 and 1.5. That is 81 and 1.5. So these design software enable me get these moments and these shear forces that I'm going to use for the design of my column. Therefore, I think I can close that and proceed with the design. I also need to assume or know the sizes of my beams. My beam sizes are 200 millimeters by 400 millimeters in the XX direction, and 200 millimeters by 450 millimeters in the YY directions. And all columns, I'm assuming I'm having a uniform column all the way from the ground floor to the top. And now we start with the actual design. Here we were just doing the summation. This was, I think, step number 2 in the design criteria, when we need to check for the column slenderness. The structure is our structure was designed as a moment resisting flame. Therefore, our columns were the ones bearing any lateral loading on our structure, because there were no shear walls or no any bracing systems. So our structure was unbraced. Therefore, we are going to design our column as unbraced. I need to consider the end fixity and bracing about both axes, and that is what I have done here. And at the top end, I assume that my column is fully fixed, and at the bottom end, I assume that my column is pinned. So we pin a column at the foundation level, and in this case we have also fixed it fully at the top level. So these two help me get conditions that I will use to determine the slenderness of my column, and this requires me to go to table 3.2. Table 3.2 3.11. Wow, where was that? Table 3.2. Almost. Yeah, it is. So this is braced and unbraced columns. A column may be considered braced in a given plane if lateral stability to the structure as a whole is provided by walls. This is what makes it braced. Or bracing, we can have cross bracings or any other system of bracing. Or buttressing, we can also have buttressing in a structure. You can Google or go and read about buttressing and find out how it's done in buildings. To resist all lateral forces in that plane. It should otherwise be considered unbraced. So if these systems are not there, then it is unbraced. And in this case, when they talk about walls, we majorly use reinforced concrete walls as compared to masonry walls. So if your structure has reinforced concrete walls, and they have been designed, let's for instance at places with lift cores or just standalone shear walls, you can also assume that your column is braced. Now 3.8.1.6 talks about the effective height, the exact effective height of a column. The effective height of a column LE is in a given plane is obtained by equation 30. That is, LE is equals to B L naught. So the reason why we are going to look for all these factors is so that we can find the effective height of our column. And in this case, because our column was unbraced, it means we're going to use table 3.20, and then we need to look at the end conditions at the top and at the bottom. And we said at the top it is fixed, that is end condition 1. Hope you also know what these end conditions mean, because we have done them in a number of videos. We have explained them. So because our top condition is fully fixed, we take condition 1, and at the bottom it was pinned. For pinned we use condition 3. Condition 3 states that the end of the column is connected to members which, while not specifically designed to provide restraint to rotation of the column, will nevertheless provide some nominal restraint. So we also consider that 3. So when you look at 3 and 1, they give you a value of B of 1.6. So 1.6 is what we are going to use here. So we will to determine the effective height of a column, we will take B, which is 1.6, multiplied by L naught. What is L naught? To get L naught, you can read here. L naught is the clear height between the end restraint, which for our case was yes, here we are. We have explained how to obtain this B. It was 1.6 for both cases because our column was having both the same condition in both cases, and the foundation is designed as a pinned, as we have stated here. So to determine the effective length, you take L naught, which is the height between the restraint, and in this case we are assuming it to be the floor to floor height. So you multiply that by that floor to floor height, and we have done that here. We have taken 1.6, that was our beta value, multiplied by 3 was the floor to floor height. So this is not entirely correct. This needs to be changed. It is the clear height between the end restraints, as we have studied from the column. Clear height between the end restraints, yes. So you take the entire floor to floor height, you subtract the depth of your beam, so that you can get the clear height of that column. So this gives you L naught, and when you do that in both directions, you get 4.08. Actually, a column can have different effective length in the different directions or the different axes. So our LE, which is the effective height, is 4.08. Now to classify the column, we look at clause 3.8.1.3, where we get that effective height in the x direction over h. H is the bigger dimension of our column, that is the dimension in that cross section of the x axis, and then you take 4.08 divided by that bigger dimension. Since our column was 300 by 200 mm, that gives you 13.6. When you do it in the other direction, the effective height was still the same, but you divide by 0.2, that is the dimension of the column in that axis, and when you do that sum, it gives you 20.4. When you look at both these two values, this is also not entirely correct. We are supposed to have LEX over H and LEY over B. So since these values are greater than 10, the column is classified as a slender column, and that is what we have done here. So that is how you classify your column, and let me show you how they here it is slenderness limits for columns, and they talk about the limits that you can achieve, and we are going to look at that just in a minute. But for now, we have already classified our column. That is clause 3.8.1.3. Let's go back. 3.8.1.3. Here it is. A column may be considered as short when both the ratios LEX over H and LEY over B are less than 15. This is for braced, but and 10 it's for unbraced. It should otherwise be considered as slender. So if these ratios are greater than 10 for unbraced, we consider it as slender, and that is what we have done. Having done that, then we need to check for the slenderness limit, which I have just shown as how it's here. Generally, the clear distance LO between the end restraints should not exceed 60 times the minimum thickness of a column. So you carry out that check. You take 60 multiplied by the minimum thickness, that is 12, and 12 is greater than 4.08. Let's look at this. The clear distance L naught between the end restraints should not exceed 60 times the minimum thickness of a column. So 60 times the minimum thickness is 12, but our effective length was 4.08. So hope you realize it did not exceed that, so this is okay. Also, we also have a clause here that talks about slenderness of unbraced columns. If In any given plane, one end of an unbraced column is unrestrained. Unrestrained columns are columns that are not restrained either the top or the bottom. And for example, a cantilever column or a column with a free end on one edge, it's clear it should also not exceed this equation here, equation 31. And because our column was restrained in both edges, in both planes, we not need to carry out equation 31 check. So that is okay, and we have classified our column as slender. From there, you determine the cover of your column. For the cover, you need to get your FCU, class of concrete, exposure conditions, and fire resistance. And from table 3.3, you will also determine your cover. And we talked about these when we were looking at the column design criteria, and we said cover can be between 20 millimeters to 50 millimeters depending on your exposure condition. Sometimes it can even get to 70 or 100. So in this case, when you look at the table 3.3, today's class is going to be a bit long, slightly long, because now we have to understand these concepts. Oh, that is very far. That is table 325. Let me see. No. 3 is about up here. Yeah, we are looking for table 3.3. Not yet there, but you have seen this before in our previous videos. Yes. So for table 3.3, you look at the exposure conditions, and we are talking about mild, because this site was in a place that is this column is not subjected to a lot of moisture or salts. And when we come to table 3.4, we also talk about fire resistance. So if I take a fire resistance of 1.5 hours, my column needs to have a minimum cover of 20 millimeters. Sorry. And you also see for mild, and the nominal cover is 25 millimeters. So for my column, I chose 30. I chose 30 millimeters, and that was tentatively good. And hope you realize I'm using an FCU of 20. For FCU, that is a class of concrete, I normally design with 20 because of the design methods that we use in our locality. To get the actual class of concrete you have designed for is normally not easy, because many contractors never do many developers never embrace doing of quality control when constructing. So we normally design with class 20 and we detail with class 25. But sometimes if you know that your construction methodology and concrete placement are good, you can just use 25. So this is just to be safe. From determining cover, you assume the diameter of your links, and for in this case we assumed 8 millimeter diameter links, and then the diameter of our main bars was assumed to be 20 millimeter diameter. From this we determine the effective depths of our reinforcement in both directions, and these are as highlighted in figure 3.22. Figure 3.22. Today we are going to have a lot of back and forth. 3.22, so that we can understand these concepts, how they are laid out in the code, and how they are going to help us when designing these elements. 3.22 is almost 0.21. 22 is the next, this one. So we need to determine this dimension. You realize that h is the longer dimension of my column and b is the shorter dimension of my column. Therefore, to determine my effective depth h, I get the depth from the extreme fiber of the surface of my element to the center of the main reinforcement on the opposite side, as also opposed to this be effective. So that is how you determine your be effective, and this diagram explains it very well. This is figure 3.22, and this is for biaxially bent column, as you can observe. With that, having obtained H and B, H is obtained, you take the entire height, you subtract the cover, and then you subtract the diameter of your link, which is 8 millimeters, and then you subtract the half the diameter of the main bar, so that you can obtain half that diameter. This will give you 252 millimeters as the effective H. For effective B, you do the same, but in the other direction, just as we have observed from figure 3.22. And these are your values. These values are important as they will help you in other procedures as we proceed. Now we get to the actual design. What we were doing, we were just classifying a column, determining cover and all that. But now the actual design begins here. In general, the cross-section is designed by methods given for short columns in 3.8.4. 3.8.4 is what we have been looking at. You realize the whole of this is 3.8.4. 3.8.4 starts where? This is 3.8.3. Yeah, so it is entirely 3.8.3 and just 3.8, the entire of it is what is helpful here. And the first thing we look at is determination of deflection induced moments. And for deflection induced moments, we use this equation as stated in the code, and we can also go there to have a look at that equation. Here it is, deflection induced moments in solid slender columns. The deflection of a rectangular or circular column, remember I told you, even if all these are for rectangular columns, there are places they have stated we can use them for a different shape, or if the clause allows, or there is nothing it is affecting, you can go ahead and use those guidelines. So the deflection of a rectangular or circular column under ultimate conditions may be taken as observed here. This is equation 32. So you get the value of AU from BA multiplied by K and H. So for BA has the value can be obtained from table 3.23 or relatively from equation 34. Equation 34 is here. You can use it to obtain BA. For you to obtain BA, you take 1 over 2000 multiplied by this is the square of LE is the effective length over B effective. As I hope you remember, we obtained B effective. Let me increase this so that it's a bit legible. So to determine that BA, this is the formula as you've seen from the code. This was equation what? Equation 34. So you take that effective length in both directions was 4.08 divided by 0.2, that is the B effective, and when you square that you get 0.20808. Alternatively, as we saw in the code, this B can be obtained from table 3.23. Instead of using equation 34, you can also use table 3.23. Table 3.23 was somewhere here. Where did it go? Is it? No. It's not 3.23. It's 3.2.1. 3.21. Sorry. Here it is. So once you have LE over B effective, you can once you calculate that ratio, you can come down here and you get your BA. So that ratio, when you calculate it, you get 20.4. So when you go to the table, 20.4 is tentatively here, and you can extrapolate to get 0.201 something thereabout. So when you look at these two values, this is 0.21 and this is 0.201. 808, they are relatively the same, so you can go with this because it is more accurate. Having obtained BA, now we need to obtain K, because H we have, this is the bigger dimension of our column. So to obtain K is actually a reduction factor that corrects the deflection to allow for the influence of the axial load. Sometimes you can conservatively take it as 1, but it is good to calculate it to determine the exact value of K. So from the code, K is right here. K is a reduction factor, that, as we have stated, and the formula is here, and it of course it has to be lesser than 1 because it is a reduction factor, and if you find the value of K greater than 1, then you have to reconsider, where NUZ is determined from this formula. Let's just go direct from this formula: 0.45 FCU AC plus 0.95 FY AC. Let me just explain the formula. 0.45 is just a factor. FCU, this is the class of concrete that you're going to use. AC, this is the area of concrete, the effective cross-sectional area of concrete, that is after subtracting the area of steel. And then 0.95 is a factor. FY, this is the grade of steel that you're using, and then this ASC is the area of steel considered. So in this case, we assumed, we considered steel that is 4%, and some of these things are assumed from experience, because we know 4% is greater than 0.04% and it is less than 6%, as we will see towards the last steps. Whatever I'm talking about is somewhere towards the end as we are designing. Let me just carry it somewhere here. Yes, maximum reinforcement is 4%. It's supposed to be 6%. Yes, and minimum reinforcement 0.4%. So this is supposed to be 6, but we will see when we get there, just in a short while. So that is 0.45 multiplied by 20. This is the class of concrete. I said I'm using 20 in the design, but I'll use 25 when I go to site because of safety. But sometimes you can just do 25 and ensure that you supervise the work so that they do that. So if steel is going to take 4%, then it means my concrete is going to take 0.96. Therefore I put 0.96. Add, this is a factor, multiplied by the grade of steel, multiplied by the area of steel, which is 0.04. This was 4%. So I have to multiply this by the cross-sectional area of my column, because these were fractions. Therefore they will subject it to this to make it the area. And when you do that sum, you get 1567.2 kilonewtons. That is your NUZ. Now N balancing, for N bal, the code also has a guideline on how to do it. That is NUZ, we are done. The approved values of K may be iteratively taking an initial value of 1. Alternatively, it will always be conservative to assume K is equals to 1. This one we have talked about, and we have also looked at BA. So for N bal, you take 0.25 multiplied by 20 multiplied by the cross section of my column, and this formula is provided for in the code. I will actually we will come across it as we proceed with this. Yeah, I did not include the clause, but we will come across it. So having obtained that as 300 kilonewtons, you now proceed to determine the N. N is the normal one, but you need to reduce your live load by 50%, and this gives you 911.7 kilonewtons. Having found this, you subject them to this formula, replacing all of them with their values, and then this will give you a value of 0.517. which is less than 1, and that is okay because we said it has to be a reduction factor. Now because we assumed 4% reinforcement, now we can determine the value of A, because we have BA, we have K, and H is the dimension of the column in that direction. So we determine AX to be 32.3 millimeters and AY to be 21.5 millimeters, and therefore we have determined A that we will use when we are getting moments in our column. Now to determine the additional moment induced during deflection, we use the formula or guidelines in 3.8.3.1. 3.8.3.1. Here we are still 3.8.3.1, and the moment is obtained by M add X is equal to N AX. That is, whatever N you have obtained up here, that is the how can we state it, the axial loading that you're going to use to get your moments, you multiply by the A, by the dimension of A, so that you can get the moment, the induced moment, the extra induced moment you're going to have in your column. So you take that N that you obtained up here, and then you multiplied by that A, which in this case you can consider it a form of eccentricity, something of that sort, so that once you multiply a loading and a length, it gives you a moment. So this is the additional moment as a result of column deflection. In this column, because it is unbraced and slender, you also need to determine minimum eccentricity, which is obtained by 0.05 multiplied by the bigger dimension of the column, and this is in clause 3.8.2.4. 3.8.2.4 minimum eccentricity. At no section in a column should the design moment be taken as less than that produced by considering the design ultimate axial load acting at a minimum eccentricity. Now that minimum is equal to 0.05 times the overall dimension of the column in the plane of bending considered, but not more than 20 millimeters. So you take 0.05, you multiply the plane considered, and in this case the plane was 300 millimeters, that is the x plane. So this gives you 15 millimeters, and the code has stated that it should not be more than 20 millimeters. Therefore we are safe up to this point. From there we now proceed to figure 3.2.1, because we said we design it like a short column but add this induced moment. Now we are going to determine the maximum design moments that we use. The maximum design moments are the greatest of these four, which is the A, B, C, and D, and I'm going to show us how to get all of them. For A, which is M2, let's or rather we can go look at 3.2.1. that figure. This is 3.2.0. this is also very helpful. This is for braced, and for unbraced slender columns it's here. So in this case we have one with a stiffer end joint and less stiffer end joint, but both of them are fixed. Ours is not fixed. At the bottom it's pinned, which is right here. So you take the initial moments from analysis and then you add the additional moments to give you the design moments. It is that simple. But you realize in my case I used figure 3.2.0 and 0.2.1. 0.2.0, it's right here, and my condition is this one. So just like in short columns, I used this so that I can get the maximum design moments that my column can experience, even if it was braced or unbraced. So this is how you go about it. M2, this is the greatest moment I got from analysis, and we had listed it up here. it's this one, the mxx. It was 85.6. And then the second B is you take mi, you add madd. Madd is the additional moment induced during deflection. So this is the formula of finding it, and then you take 0.4 multiplied by m1. In this case our m1 is 0. You add 0.6 multiplied by m2. So since m1 is 0, there it is. And once you add 0, you multiply 0.6 by the moment, you get these values. This gives you the mi, which you need to add this additional moment during deflection to get these moments. So that is how we go about B. For C, remember we have determined the minimum eccentricity. So you multiply it by the load that you use to get these moments, and here it is. That was 15 divided by 1000 multiplied by 911.7. So you get 13.68 kilonewton meters. From there you get to D. D is m1 add half of the additional moment. So once you do that, you get 100.3 kilonewton meters, and for my you get 11.2 kilonewton meters. Therefore, the design moment used for this design are the maximum, the greatest value obtained from these steps here. So when you look at the moment in the x direction, the greatest is 100.3 kilonewton meters, and that is what you use for your design. For the y direction, at this case it is 11.2, and this was no, this was y. This is not x, this is y. This is 20.44. Yes, so 20.44 is greater than 11.2, so that becomes the greatest, the maximum moment in that plane. Having obtained the moments, now you look at clause 3.8.4.5. Remember, all those formulas I have shown, I explained here using this diagram, because the maximum design moment envelope of such a column is as shown here. So looking at 3.8.4.5, 3.8.4.5. 3.8.4.5, where did it go? Just a second. Yeah, this one. When it is necessary to consider biaxial bending, and in the absence of more rigorous calculations in accordance with 3.441, symmetrically reinforced rectangular sections may be designed to withstand an increased moments about one axis given by the following equations. This is because one axis has more greater moments than the other one. So when you do mx, that is the moment on the xx axis, divided by the effective depth, the bigger effective depth, it is when it is greater or equal to the one in the other plane, that is in the yy plane, then you consider the use of this equation, this one right here. Yes, where you mx prime is given by mx plus beta h prime over b prime multiplied by the moment in the yy direction. That is equation 40. And for equation 41, it is the vice versa. When mx over effective h is less than that in the yy direction, then you consider this equation, equation 41. So in this case, mxx was greater, so we consider equation 40, and these have been explained. Beta is the one we obtained earlier on, and these other values are as explained earlier on. So once you do that, this one was 398.01 and this one was 134.474, and you see this is greater than this, therefore we pick this equation 40 as stated for in the code. Having picked equation 40, now we need to determine what we are going to use to determine reinforcement in our column. And for this, we look at 3.22. That is table 3.22. Table 3.22. So we need to determine n over bh FCU, and we get beta from it as we proceed with our design. So for this, n was the axial loading that we used to get our moments, and then bh, these are the dimensions of our column multiplied by 20. Remember I said here we are going to use 25, but I use 20 so that I'm safe, because it is very difficult to control the quality of concrete on site. This gives me a value of 0.76. With 0.76 I can determine now my beta. So once you come here, you get 0.76. it is over 0.6. Therefore, what is the value of my beta? It is 0.3. Just a disclaimer, remember we have this beta that we have obtained from table 3.22, and there is the other beta we were obtaining. Let me get it. This one, this is beta A. These two values are different because this one was used way earlier on here when determining the deflection induced moments. So for this case, we are determining this beta from table 3.22. So we have found that if it's greater than 0.6 or equal to that, it is 0.3. So if my beta is 0.3, since that clause has been stated, now I have everything here and I can input them in my formula to get 110.47 kilonewton meters. Now that mx is the maximum design moment that my column is going to experience in that plane, and this is the moment that now I'm going to use to get my reinforcement. So let me just go through again these moments, because this is where most students make mistakes or give up when looking at the design of columns. Since our column is slender and it's not braced, we need to determine additional moments that are induced during deflection. And for the additional moments, I've explained that you need to find the m-add. For m-add, these additional induced moments, you determine the length, which is determined by this formula in clause 3.8.3, and that you have to get A, you have to get K and H. Having obtained that, you multiplied by n. N was the axial load that you were using to get your moments. So you get these values as stipulated here, and then you check for minimum eccentricity, you get it to be 15 millimeters. From there, you determine the maximum design moment using either A, B, C and D, and whichever values are great in terms of mx and my, you list both of them down, because you're going to use them both to determine the maximum moment that your column is going to experience in one plane. After that, you equate them using the consideration in clause 3.8.4.5, and since this mx over h of effective h is greater than my of effective b, therefore you use this equation. For you to use this equation, you need to determine beta, because you have all other parameters. For you to determine beta, that is the one in equation 40, you use table 3.22. But for this, you have to have a value from this formula so that you get your beta. And once you get that, you get the beta, you replace it back in the formula, you get the maximum design moment as 110.47. So now this is the final moment for design. From there, you now you need to now go to the charts and start selecting your reinforcement. From the charts, what is it required of us from the charts? Just before looking at the charts, you need to get N over BH. N is the axial loading that we have used, and then BH is the dimensions of the column in both directions, the cross-sectional area of the column rather. So that gives you 15.195. And then next is the moment, the maximum design moment that you've obtained. You divide by BH squared. B is the smaller column dimension, H is the bigger column dimension. So once you do that, you get 6.14. These are important for you to get your design moments, to use the charts to determine the reinforcement in your column. And for D, this is the effective depth of our reinforcement. We determined it to be 252 in the XX axis and 152 in the YY axis. So you also need to get D over H. This is to help you determine the chart to use. The charts are classified in terms of the ratio D over H. So when you do D over H, you get 0.84. And because they are in factors of 0.05, you can say 0.85. Other parameters you need to consider before looking at the charts is the class of concrete, the grade of steel, and that D over H. And of course you need to calculate these two so that you can be able to determine your area of steel required. So I wanted to explain, you realize that I have been using 20 for the concrete grade, but here we are now using 25 because the charts are prepared with 25. The 20 I was using is so that we can be safe, but as I have been stating all along, you can still use 25, but ensure that this class is achieved on site, because the reason why most structures come down is because number one, concrete, people have focused so much on steel that they forget to supervise or to ensure quality control when dealing with concrete. And when we looked at it, we found chart number 23, that is in the BS8110 part 3. Now since we have been looking at part 1, now this is part 3. Part 3 is right here, which we stated that we will be using. And it starts with the doubly reinforced beams. It actually starts with singly reinforced beams, it gets to doubly reinforced beams, and then it gets to rectangular columns. So you realize the N over BH we were calculating is here, N over BH. M over BH squared is here, and then the other parameters, that is the FCU, the FY, the D over H. So this is okay, it's okay, it's okay, it's okay, but D over H, this one is 0.75. So we move, we confirm this one is 0.8, we still move 0.85. This is the one we're looking for. There are other charts still 0.9, 0.95, 0.75 for rectangular columns, but this is concrete class 30. Yeah, so ours is 0.85 right here. So once we get here, we have a value of N over BH and M over BH squared. So N over BH is 15.195 and this is 6.14. So this is 15 and this is 6.14. So I'm going to assume it is exactly 15 and 6. It gives, I get here, I don't know whether I can expand it. Yeah, this is 15. This is how the chart looks, and it's in page 24. So this is 15 and this is 6. We come here, so this is the area, this is the ratio we are looking for at this point, and when we use that, now that is 100 the area of steel over pH. It's been stated here. You find it as what? This is curve number 5. So this is around 5.2, 5.3, something there about. So this is approximately 5.3. So if I have this as 5.3, therefore I can determine my area of steel required. Let me repeat the process. Remember, I have already calculated N over BH and M over BH squared, and I have come to BS8110 part 3 with the concrete class of 25, yield of steel of 460, and D over H of 0.85. I have selected chart number 23 as the chart to use. Having selected that, I need to come to M over BH squared, which was 6.1, and N over BH, which was 15, and I get to 5 point something. So this is how you read it. You look at these curves, these continuous lines. Yes, so my point of intersection is between 5 and 6, but is closer to 5 than to 6, so I approximate this value from here. So this is 5 point, let's tentatively call it 5.3. So with 5.3, I'm able to get my area of steel by feeding it into this formula, and I have my B and H, and I get 3180 millimeters squared as the area of steel required. Since I have this as the area of steel required, if I provide 4 32 millimeter bars, I'm going to have 3220 millimeters squared, which is greater than this. Therefore, that is okay. From that, I remember I had assumed 20 millimeter bars. I had assumed a class of concrete of 20, and I had made many other assumptions that might not be true up to now, because here we have provided 32 millimeter bars and we assumed we are going to use 20. So now I have to revise my K so that I can find out whether my reduction factor is greater than 1 or it's less than 1. Therefore, to revise my K, because I have the actual values, I still use the formula I used earlier on, but now I use the actual values I have. For instance, NUZ is 0.45, and we saw the formula from this equation, from this clause, multiplied by the concrete class. Here I'm now using the concrete class I'm going to use on site, multiplied by the area of concrete. Now the area of concrete, it is easy to determine because you take the cross-sectional area of your element, you subtract the area of steel, and that is how you get the effective area of concrete. And then you add 0.95, multiply the steel yield strength, which is 460, and the area of steel, which is that, and that gives you 2045.915 kilonewtons. So the revised NUZ is 20.45, and the one we determined earlier is 1567. So you realize it's different. Yeah. So having obtained that, you also get the Embark, which is actually normally 0.25 FCUBH, and that gives you 375, and once you feed it into K, you get 0.679, which is less than 1, and that is okay. Therefore 32 millimeter bars are sufficient. From there, you proceed to carry out the shear check. For the shear check, you use clause 3.8.4.6. let's look at that. 3.8.4.6. remember, today's class is slightly long. It feels long because we are explaining these things, looking at the code and studying it carefully. So we have shear in columns. The design shear strength of columns may be checked in accordance with 3.4.5.12 for rectangular sections in compression. Let's reread that again. The design shear strength of columns may be checked in accordance with this. For rectangular sections in compression, no check is required. our section is rectangular, and therefore no check is required, but it has to meet this condition: m over n does not exceed 0.6 h. M over n does not exceed 0.6 h. Therefore you take the moment in both axes, and then you realize it is less than 0.6 h, which means we don't need to carry out a shear check in our columns. And then there is also another continuous that and v does not exceed the maximum value given in 3.4.5.12. v, as we saw in other elements, is obtained by this formula, and what they provide that it should not exceed is either 0.8 multiplied by the square root of FCU. When you carry out this calculation, when FCU is 25, this value I think comes to around 4. So either 4 or 5, our value must not be greater than that, and when you do the math you realize both values are less. Therefore no shear design or extra shear check is required for our columns. And let's just look at that code, that clause that the code has stated: 3.4.5.12. 3.4.5.12 here. Shear and axial load. The design shear stress can be supported by a section subjected to shear and axial compression without shear reinforcement can be calculated from equation 6a. Both adverse and beneficial load combination should be considered, and check that table. But the limit they are talking about, it's here. V should not exceed 0.8 the square root of FCU, or 5 newtons per millimeter squared. So if V exceeds that, then it means we need to provide shear reinforcement or design it to resist that. So in our case, there is no shear check is necessary for this column. From there we move to minimum reinforcement. Minimum reinforcement is given in clause 3.12.5.4. Yes, in this table. So for minimum percentages of reinforcement, we consider which element we are working on. We are working on compression element, that is a column, and then A is a rectangular column or a wall. So the formula is this definition of percentage formula, and then the minimum for 60 Newton per millimeter is 0.4%. So the minimum reinforcement in such a column is 0.4%. Therefore our reinforcement is which percentage? To get the percentage of our reinforcement, we just determine the area of steel of our reinforcement divided by the cross-sectional area of concrete, and we multiply that by 100 to get 5.36, and actually that formula is basically this: 100 multiplied by the area of steel divided by the area of concrete, and divide by the cross-sectional area. And we are actually not looking at the effective area of concrete, we are looking at the cross-sectional, the entire cross-sectional area. That is the difference, because up there is a place we looked at the effective concrete area. So from there we determine it to be 5.36. We also check whether it passes the maximum reinforcement check, and as I had stated, it's supposed to be 6% from the code. I think we can look at it. Which clause was that? It's here. Maximum areas of reinforcement in members, that is clause 6.12.6.2 when we talk about columns. Here the longitudinal reinforcement should not exceed the following amounts, calculated as percentages of the gross. This is the gross cross-sectional area of concrete. Gross, we mean the entire. Net, we mean just concrete having subtracted still. So for vertically cast columns, the maximum area of reinforcement is 6%, which I stated that maximum reinforcement should be 6, not 4. Actually, I remember, probably because I initially provided 4%, maybe that is what I had forgotten and written this. So this is supposed to be 6. For horizontally cast columns, it is 8, and for laps in vertically or horizontally cast columns is 10%. So for the minimum area of reinforcement, our column has passed. Maximum area of reinforcement, it's 5.36 as compared to 6. Therefore our column has also passed. What about the area of reinforcement around laps? When we do lapping, we actually lap all bars, but it's not advisable to lap all bars at the same section, as we had stated in one of our old videos, that you need to stagger your bars. But in this case, area of reinforcement around laps is, you calculate the area of reinforcement of steel multiplied by 2, because I'm assuming I'm having the weakest joint where I'm lapping all of them at the same location. Therefore that gives me 6440. When I divide by 6440 divided by the entire gross cross-sectional area of my column, I get 10.7%, which is greater than 10%. Therefore I am forced to increase the column size. This shows that my column size is insufficient and I need to increase it because of this check of area of reinforcement around laps. It needs to be less than 10%. Though if I am limited to just using this size, I can still use my reinforcement, but ensure I do not lap all my bars at one place. I can lap maybe half of the bars here, which means you need to multiply this by 1.5, and I'm sure that will be less than 10%, and I proceed. Therefore, if I do that, I have to detail my element very well and also supervise it so that they do not mistakenly lap all bars at the same place. But for best practice, increase the size of your column so that it considers this check of area of reinforcement, maximum area of reinforcement around laps. Therefore, to increase the size, I decided to use 350 by 200. And this gives me, initially it was 6440. No. Here we have a problem. This is also not 10.7%. This is this is not correct. It should be deleted. Yeah, this is the correct thing. This is also not correct. Yes, it's supposed to be 6440, which is the maximum area of reinforcement at the laps, divided by 200 by 350 multiplied by 100. When you do this, it gives you 9.2%, which is the value here, and that is less than 10%. Kindly ignore all this other information, but carry out the math afresh and it will be less than 10%. Therefore it is sufficient. From there, I finally get to my last check, where I look at the containment of my reinforcement, and that is in clause 3.12.7.1. 3.12.7.1, we talk about when part of all the main reinforcement is required to resist compression, links or ties at least 1/4 of the size of the largest compression bar, or 6 millimeters. Whichever is greater should be provided. Therefore, to check whether my links are sufficient, we've said it's 1/4 multiplied by my largest bar diameter, which is 32. Therefore, the minimum bar I can use in this column is 8 millimeters, and it is okay, just as I had assumed earlier. To get the maximum link spacing, it is highlighted here that should maximum spacing of 12 times the size of the smallest compression bar. Therefore, I consider the smallest bar in my column, and in this case, because I just have 32 millimeter bars, I multiply that by 12 to get 384 millimeters. Therefore, I consider having 8 millimeter bars that are spaced at 200 millimeter center to center. Therefore, I have checked the containment of my reinforcement. From there, I sketch my column and I take it to site as a working drawing so that it is able to guide those laying the steel fixers and the contractor. So this is just a sketch of my column, and the cross section is 200 by 350. I have 8 millimeter links tied at 200 mm spacing. 12 is the barcode, and then 08 is the barcode. When I do the entire cross section of the column, you will see how 08 comes in. And but just a question out of curiosity, there is a check I have not carried out. What is the minimum distance from one bar to the next? What is the minimum and maximum distance that we are supposed to have? Therefore, that is a question meant for you. Go carry out research. The same code talks about the minimum spacing that you can have between these bars. That is considering your maximum aggregate size and your method of placement of concrete and all that. Because if you leave a very small space, then you're going to have honeycombs in your structure. But the code talks about that, and that is assignment you need to check out. But I found this research from Petra University, and it was from the book Concrete Elements, that is page 119. And I hope this extract can explain all these things clearly, and we can go through it very fast. No maximum spacing is actually stipulated in British Standard 8110 for the main bars in a column, other than those implied by the recommendations for containment of compression reinforcement, which we have already looked at, including the minimum size of my link and the maximum spacing I can have. However, for practical reasons, it is considered that the maximum spacing of main bars should not exceed 250 millimeters. Therefore, consider this and ensure it does not exceed 250 millimeters. For lateral reinforcement, it is commonly referred to as links or ties, or sometimes binders. So when you get ties, binders, links, they mean the same thing. Its purpose, let me increase this, maybe it's not legible, I'm struggling. Its purpose is to prevent lateral buckling of the longitudinal main bars due to the action of the compressive loading from the top and the subsequent spalling of the concrete cover. And this is how, basically this is what we mean, that we have the main reinforcement bars like that, and these ones have no link, so they are free to move. But the work of these links or ties is to keep them in place so that they do not move as a result of the compressive action of the loading of the column. And as you can see, for our case without the links, applying the compressive load, this is how buckling will occur when our reinforcement fails, because there are no ties that can tie them together and keep them in place. But because of the links, the lateral ties prevent lateral bucking of the main reinforcement bars, as observed here. That is why you also need to maintain the minimum, the maximum spacing required. Then the diameter of the lateral ties must not be less than 1/4 the size of the largest main compression bar, and in no case less than 6 millimeters. And this one we have studied as the last bit of containment of bars. The maximum spacing of lateral ties must not be more than 12 times the diameter of the smallest main compression bar. This one we have also discussed it. Furthermore, it is common practice to ensure that the spacing never exceeds the smallest cross-sectional dimension of the column. Furthermore, it is common practice to ensure that spacing never exceeds the smallest cross-sectional diameter of the column. I have a question. You realize maximum link spacing was 384, but I considered 200 mm. You see, this is way more safer. What did I use when I was considering this? On studying this literature, it states that furthermore it is common practice to ensure that the spacing never exceeds the smallest cross-sectional diameter of the dimension of the column. Therefore, my column being 200 mm by 350 finally, is that I consider now to use my bars at 200 mm center to center. Therefore, that is what I used to determine that. A main compression bar contained by a link passing around it and having an internal angle not more than 135 degrees is said to be restrained. So a bar that we have enclosed and we have these links at an internal angle that is not more than 135 degrees is restrained. So these bars are restrained. But when you look at these, is these and these restrained, or we just have the corner ones restrained? Let's continue reading. BS8110 stipulates that every corner bar and each alternate bar should be restrained. So every corner bar and each alternate bar should be restrained. So if a column was having more than 4 bars, you will realize that they always will be even numbers. They cannot be an odd number, because we have to have, there is an assumption we made just way before beginning. The section is symmetrically reinforced. Yes, the section is symmetrically reinforced. That is why we cannot have odd numbers, but we can have even numbers of reinforcement. So the code is stipulating that these and these must be contained. How do you contain them? Immediate bars may be unrestrained provided that they are not more than 150 mm away from the restrained bar. So if these middle bars are the distance between the middle bars and a restrained bar is more than 150, therefore we need to restrain it. But if it's less than 150, we can still tie it to this main link and it will be okay. So how do you restrain it? The forms of restraints are as shown here, and you can use your you can restrain them and then provide for this in the bar bending schedules. The compression bars in a circular column will be adequately restrained if circular shaped links are provided passing around the main bars. Lateral reinforcement arrangement to satisfy these requirements are illustrated in these figures. So this is what we mean. But for circular, you can actually have that, but determine if this distance is greater than 150, have restraining bars on your column. Compressive ULS. The compressive ULS analysis for short braced columns given may be basically divided into 3 categories: short braced axially loaded columns, short braced columns supporting an approximately symmetrical arrangement of beams, and all that. I believe this one we looked at it when we were talking about these cases, these design cases right here for compressive ULS. Therefore, this research or this guideline by the Petra University in the book Concrete Elements brings us to the end of our study today, and I believe we have understood how to design a column and how to determine the size and finally get the reinforcement and carry out all those containment checks and the spacing and all that. And finally, now this is how a drawing looks like, a column drawing. There are very many ways you can draw it, as long as it's able to effectively communicate what you're doing on site, you are good to go. So in this case, you need to label it. This is column C4. When you will look at the plan view of this drawing, the floor plans, this is what you will see, and it is 1 in number. This will help you when preparing the bar bending schedules, so that you know how many bars you're cutting and bending. And you also need to just provide the distance, the dimension of the column below the ground, and this is normally determined on site. DOS means determined on site. This shows that our column is continuous, and therefore these details at this place are provided for in the footing cross section the way we do it, but sometimes you can draw it and attach the footing to it at the same time. Also, you also need to show the cross sections at every column, but I wanted us to show us this so that I can show you there is something missing. Once you do this is a bar from the substructure. You also need to dimension the overlap length. The overlap length is very important. You need to dimension it so that it's clear to the fundis or to those who are fixing reinforcement on site of how to do it. And you need to provide the cross section. So in the cross section we provided in our drawing, you realize we just had the barcode 08 and we did not tell you which bar it was. But in this drawing now, it tells you that here we have 4 T32 bars and their barcode is 08. So when you come to the cross section, you realize 08, this is where you get the size of the bar. And of course we have the column cross section and the floor to floor height. And at the center of the column you also do the total number of links, and you show their spacing, but those are also provided in the cross section. And that is how you do it. So remember, these overlaps are not dimensions, and it's important to dimension it. And for our structure here, it was going all the way up to the parapet level, and at the parapet level our column was reducing in size. But the main important thing was the design of the column at the ground floor, and we decided it to be uniform to the top floor. Sometimes because of economy, you design a column, if assuming you are designing a 10-story structure, designing the ground floor column and replicating the details to the other columns might not be economical. So what you do, you segment your structure maybe after every 3 floors, identify the conditions there, and determine the design of the column. You can even reduce reinforcement going up and reduce the column sizes going up, but you have to design for you to do that. You cannot just provide without designing. Therefore, this is the end of today's engagement. We have designed our column, and I hope that you have learned something. It has been a slightly longer class as compared to the other components, but it's beneficial because it has quite good information that you need when designing columns. Therefore, thank you very much, and we wish you well as you proceed to go and design columns. May the good Lord bless and keep you, and may He flourish the kingdoms that you lead as structural engineers. God bless.